Rudolph the red-nosed reindeer had a very shiny nose. Woo! Thanks for being here. So we are finishing off here 5.5, then getting ready with our practice test. Let's see, starting here for the video. Okay, that's helpful. So we're going to start off here number 15 next. Don't forget to factor the top and the bottom, right? Factor the top and the bottom. So if you don't remember the steps for all the graphing rationals part, let me show you in our books. So right here is where it talks about it. Yeah, there's like nine steps. Whoa! So you have to completely factor the top and bottom. Then list the domain restrictions. That's what makes it 0 in the bottom. Reduce the function if possible, and if you can't reduce it, that means you canceled something on the top and bottom. And the thing that canceled on the top and bottom is called the whole. Right? It's called the whole. Put the restricted x value into the reduced function and solve for y. And that's going to give you the whole. It's going to give you the xy value, the whole. Whatever's left in the bottom is the vertical asymptote there. Vertical asymptote. And then in behavior, so if it's just a line or a parabola, you can go up, up, or down, up. But basically, if there's something in the top and the bottom, then you're actually going to list the horizontal asymptote, right? And then find the y-intercept and list it at that point. So you have to set x equal to 0, and then find what y is, 0 comma y. It can be only one. Now to find the x-intercept, you set y equal to 0. So that'll actually come from the top, right? So you actually want to define the x-intercept. So to find the x-intercept, you actually want to set the top equal to 0 is what you want to do to find that x-intercept, right, as an xy coordinate. And then if necessary, you can use an additional point to help you know if you're above or below the x-axis when graphing. Also, if it's even or odd in the multiplicity in the bottom. So is your vertical asymptote, does it have a power like parentheses to the first power, odd? So that would be like down, up, or up, down. Or does it have in parentheses like x minus 2 all squared? And so squared would be even, and so that'd be like up, up, or down, down. So good. So and then also for the horizontal asymptote, this guy. So there's actually 3 things that we learned. And those 3 things that we learned are, for the horizontal, this is from our last thing. So we learned if the top powers are equal to each other, then we're going to use the numbers in front. Horizontal asymptote, y equals 3/2. If the top power x over the bottom power x squared, so if one is, if it's bigger on bottom, Bobo. So that means bigger on bottom equals 0. So that would be the horizontal asymptote of just y equals 0, which is along the x-axis. Along the x-axis. Along the x-axis is what's going on there. Along the x-axis. Okay, or if, last but not least, if it's the top power that's greater than the bottom power. So if the top power is greater than the bottom power, then y equals none or slanted, right? Y equals slanted or none. Basically, there's no horizontal, but there is a slanted asymptote there, right? Cool. So I just wanted to share that with you. Here we go. Here's some of the notes we did. Example number 2. Let you pause and look at that for a second. Go ahead and pause me. If you were here for example 2, take a look at that. Okay, so back to our homework. So we're going to go ahead now and factor the bottom. So we get x and x. Factors of 12 are what? 3 times 4. Sign of the middle term goes with the bigger number. So there we go. Nice. So then it does look like we did factor it correctly. Good. 4x minus 3x is 1x. So I think we have 2 domain restrictions, right? We have 2 domain restrictions. X can't equal a positive 3 and a negative 4, right? Now we do have something that cancels on the top and the bottom. Do you remember what it's called? What is it called? It factors on the top and bottom. It's called the donut hole. Whoa, donut holes. Here, you get one. Here you go. Would you like a donut hole? Yeah, here you go. That was really good, right? So the thing that cancels on the top and the bottom is called the hole. So we have an x plus 4 and an x plus 4 that cancel. So that's called the hole. So we have x plus 4, set that equal to 0, minus 4 to the other side. So x equals negative 4 is the hole. Now we got to find the y value of the hole. So what we do to find the y value of the hole is, there we go. So we take the reduced form, which is 5 over x minus 3. Y equals 5 over x minus 3. And we plug in the x value of the hole, right? So we go ahead and take that x equals negative 4, right? X equals negative 4. And we plug it in there. We plug a negative 4 in, so we get 5. We get 5 over negative 7. So negative 5/7. So negative 5/7 is the y value of the hole. So that's back 1, 2, 3, 4, and then down negative 5/7, which is almost negative 1. So right about there. And there's our hole. There's our hole. So we found our hole. The thing that didn't cancel on the top and bottom is your vertical asymptote in the bottom. So the thing that didn't cancel is the x minus 3, or x equals 3. So we have a vertical asymptote at 3. Let's see here. So our x-intercept, we can take the x-intercept, and we set y equal to 0. But the tricky part about that, interesting, is that when you take that function, y, whatever's left, so that's 5 over x minus 3, right? So 5 over x minus 3. And so when you set y equal to 0, right, you got to solve for x. Well, how do we get x out of the bottom? We go ahead and multiply it over to the other side. So x minus 3 over 1, x minus 3 over 1, and so that gets it over to the other side, but x minus 3 times 0, x minus 3 times 0 is just 0 and goes away. We're left with 0 equals 5. And so 0 equals 5, that doesn't even make sense. So 0 does not equal 5, so that means x-intercept is none. Whoa, no x-intercepts. Now there's probably a good reason why. There's probably a horizontal asymptote in the way. Let's find out. But first, let's go into the y-intercept. So to find the y-intercept, you set the opposite letter x equal to 0. So we go to our original function there, which is y equals 5, the reduced function. So y equals 5 over x minus 3. And we set x equal to 0. So then we get negative 5/3. So we have a y-intercept at 0 and then down, so negative 5/3. That's like 1 and a bit, I think. Let's take a look at that. So negative 5/3 is negative 1.66. So that's right about here is where our y-intercept is. And so the reason why we don't have an x-intercept is because when you look at the end behavior, so y equals 5 over x minus 3. And so end behavior, we do have a function right? We do have 5 over x minus 3. And so that means we do have a horizontal. And since we do have a horizontal asymptote, we're not going to list the up, up, down, down. We're not going to do up, up, or down, down, or down, up. We're going to actually list the horizontal asymptote. That helps us better with graphing this. And so a horizontal asymptote has to do with the top power. Well, there is no top power, it's just a 5. Technically there is. There's an x to the 0 power, right? Because anything to the 0 power is just a 1. And since anything to the 0 power, even x to the 0 power is just a 1, so that means technically there is an invisible 1 up there, and it is x to the 0 power. And so that means that top is less than bottom. And since top is less than bottom, then y equals 0. Right? Bobo! Bobo! Bigger on bottom, y equals 0. That's bigger. 1 is bigger than 0. So bigger on bottom equals 0. And that's why we don't have an x-intercept, because there's a horizontal asymptote running through the x-intercept, the x-axis. So we have a horizontal asymptote at y equals 0. Okay, so now we're going to graph it, and we're going to let the hole be our guide, let the x-intercept be our guide, or y-intercept, sorry, not x, y. Let's use hot pink magenta. Okay, so we're going to go along this horizontal asymptote. We're going to jump over our hole, go through our y-intercept, and go down like this. And then since x minus 3 is to the first power, which is an invisible 1, so that's odd, we're going to go opposite directions. So since we're going down, we're then going to go up on this side of the asymptote. And so that'll go this way, and that'll go this way. And if you're not sure, you could do a extra point, right? Additional points. So you could do you could do a check. You could do a test point. That's what it's called. You do a test point. So say that after 3 is maybe like 4, for example. So let's say x equals 4. And so when you plug it in, 5 over x minus 3 is our equation, and you plug a 4 in there. So 4 minus 3 is 1. So you get 5 over 1. So that means over 4 up 5. 1, 2, 3, 4, 5. So our graph is even off, right? Because that's too high, too fast. Should actually be right there. But it's still good enough. And so what that tells us with the 5 over 1, right? So the 4, 5, the point 4, 5, that's our test point. That's our test point. It tells us we're above. We're above the x-axis with our graph. And also because the vertical asymptote was not an even power, down, down, nope, it was opposite, so down, up. Okay, there we go, we did it, there's our graph, woo! And again, we had a horizontal asymptote of 0, and a horizontal asymptote of 0 is what we had there. Cool. Okay, so I'll go a little bit faster on this one, number 17 next. Okay, so then we're going to factor this one. Hey, I feel like I've seen this one before. Have you seen this one before? I feel like I've seen this one before. Pause me and try 17 on your own. I feel like I've seen it before. Go ahead and pause me. Pause me. So we have pause me. Try it on your own first. Try 16, 17 on your own. So the domain restrictions are x can't equal a positive 3. Because a positive 3 would make a 0 in the bottom, can't divide by 0. I was going to have a vertical asymptote at x equals 3. At x equals 3, so x minus 3, but I see that it cancels and it's a hole. So this cancels with this one, and that's our hole at x equals 3. And so what's left are our function that's reduced. So that's going to be just y equals x plus 3. And so we take our whole of our x value and we stick it in there. So we get 3 plus 3 is 6. And so our y value is 6. So over 3, up 1, 2, 3, 4, 5, 6 is where our hole is. At 3, 6, that's our hole. Our removable discontinuity. Okay, so then the vertical asymptote, we have none. We don't have them because they canceled out on the bottom. They're all gone. X-intercept, you set y equal to 0. And so in this case, we have y is equal to x plus 3. And we can actually do this one. We don't have to worry about the bottom. Let's see. So we plug y equal to 0. We solve for x by minusing 3 to the other side. And so we get x equals negative 3 is what we got there. So x equals negative 3. And y, of course, we said equal to 0. So y equals 0. And so we have the coordinates negative 3, 0 is our x-intercepts. Negative 3, 0 there. Now to find the y-intercept, you set x equal to 0. So y equals x plus 3, set x equal to 0. And so when you set x equal to 0, you get y equals 3. So 0, 3 is our other. So 0, 3 is our y-intercept. So 0, 3 is our y-intercept. So that's going to be 0 up 3. Y-intercept, 0 up 3. Okay, and behavior. So this time our equation doesn't have a denominator. So we don't have a horizontal asymptote. I mean, you'd say it's slanted, I guess, along the line. I don't know. But yeah, so we'd say end behavior is going to be down and then up. And the reason why is because it's x to the first power and x positive. X to the first power is going to be positive x to the odd power, which is down up, So now we're going to go ahead with our slope of 1 over 1. So over 1, over 1, over 1, up 1. Okay, there we go. So over 1, you stop it. Over 1, up 1, over 1, up 1, over 1, up 1. So there's our line, Jump over the hole. Make sure you jump over the hole. There you go, jump over the hole. And then back this way. Cool. So there's our graph, you guys. It's a line with a hole in it. That's crazy, right? Okay, pause me. Try the next one on your own. Pause me. So here we go. 18, you got this. So it says here, using graph calculator, rotation, and where x is the order size, x has to be greater than 1. Using graph calculator to graph the cost function, use the window. From the graph, estimate the order size that minimizes the cost. So hint, find the minimum. So yeah, so you're basically just using a graphing calculator on this one. And I can see you, yes, using this on the test. So make sure you know what you're doing for the test. Can you graph? Can you graph a function? So we have clear, we have 100, parentheses, another parentheses, what the? Okay, it's a little tricky here, let me see. So we have parentheses 200 divided by x squared, lots of parentheses going on, because we don't want to mess this up at all, plus another parentheses x divided by another parentheses x plus 30, close parentheses, there we go, close parentheses again. So basically we had to use a lot of parentheses. We had to use a lot of parentheses because there's 100 multiplying that whole thing. And we also had a fraction and a fraction with a plus. Need parentheses around that on the bottom. So definitely needed lots of parentheses there. Okay, so we're going to try to graph this guy. And I don't see our graph. So we might have, maybe it's really high up in the air. So let's try changing our window. It's the window button. And maybe our y maximum is really high in the air. Like maybe 100 or something. Wow, still don't see anything yet, huh? Interesting. It is being graphed, so that's good. Let's try zoom 6. Let's try zooming out. Let's try zooming out. Oh, we see something. Try zooming out again. Whoa, we see something else. Okay. So we had to zoom out twice. You had to zoom out twice. And so they want you to find the minimum, right? From the graph, estimate the order size that minimizes the cost. So if we push the trace button, looks like right about here is where it minimizes it. So you go second, calc. We're going to go to minimum, enter. We're going to go to the left of that minimum, enter. We're going to go to the right of that minimum, enter. And then you're going to guess. Right about here is where the minimum is. And so from our calculator, we get a minimum of 40. So 40.44. So we get a minimum at x equals 40.44. We get a minimum. Right? So the ordering and transportation costs, $1,000 for components used in manufacturing. A product is given by that equation, where x is the order size in hundreds. So where x is the order size in hundreds. So use the graphing calculator to graph the cost function. Use the window x minimum, x maximum from the graph. Estimate the order size that minimizes the cost. Yeah, so x equals 40, and it says in hundreds. So 40 hundreds, I guess, which would be 40,000. No, it'd be 4,000, right? Because hundreds is 2. Yeah, so it should be, I think, 4,000. We'll just say 40 hundreds is better. So 40 hundreds is what's going to minimize, that's going to minimize the cost. Okay, last but not least, I wanted to help you on that one because that was kind of a tough one. So, and we'll be on the test, whoa! So what percent is 40 out of 28? What percent is 40 out of 28? Well, let's see, 40 out of 28, that seems kind of silly, doesn't it? Because that's like a, what'd you call it? It's like a, I don't know, 40 out of 28 is going to be definitely bigger than 100%, as you can see. And so if we divide by 2, maybe, divide by 2, so that gives us 20 out of 14. Oh, divide by 2 again. So that gives us 10 out of 7. And so, yeah, so what's that as a percentage? I don't know, that's tricky. So it's definitely going to be a greater than 100%. So 7 goes into 10 once. And so that's 7 minus it, so we get 3. We bring down a 0. 7 goes into 30 4 times. 7 times 40 is 28. So minus, so we get a 2. Bring down the 0, goes 2 times. Yeah, so we're looking like at probably 142 point something percent there is what we're looking at. If we just would have used our calculator there, we would have gone 40 divided by 28. And yeah, 142.85, which is 6/7. All right, thanks for watching. Get ready for our practice test. You got this. Ace the Unit 5 test. Thanks for watching. See you soon. Had a very shiny nose.